Okay, so this next section goes into the chemistry of life. So we'll start with a basic introduction to chemistry, and then we'll go on to biological macromolecules, which is a little bit more of the biochemistry. This is a list of the learning objectives. If you'd like to read through them, you can pause the video and take a moment to read them. So the first section, we're just going to do a basic introduction to chemistry. So to start, we're going to start off with some definitions. So matter. Matter is anything that occupies space and has mass. So everything on Earth can be considered matter. So that's any air that we breathe. We are considered matter. The pencil that you may be writing with right now is considered matter. So anything that has mass and takes up space is considered matter. Energy is required to perform work. Work is usually going to be some type of movement. So you have potential energy. Potential is the potential to cause a movement, while you have kinetic energy. And when you have kinetic energy, you're actually performing the movement. Later on in this semester, we're going to learn a lot about energy, and the basic molecule for energy is adenosine triphosphate. And that's ATP. We're going to learn a lot about this molecule, how it's regenerated, how it's broken down, and what it's used for along the lines of energy. Force causes a motion. So the physical definition of a force is it causes an object to change its velocity. So force is a little different from energy. Energy is the ability to do work, while force is actually causing an object to change its velocity. In this class, we're not going to focus too much on force. Force is more for a physics class, but we will be talking a little bit more about energy. So when we talk about chemistry, chemistry focuses on the elements that are listed on the periodic table. So what an element is a substance that cannot be broken down further because it's made up of one type of atom. There are 92 elements that are naturally occurring, and 6 elements make up 95% of the body weight of organisms. So carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, and then there's a bunch of man-made elements as well. So the approximate percentage of elements in living organisms is listed below here, compared with atmosphere and the Earth's crust. So we have a lot of oxygen inside of us. Then you see carbon, hydrogen, nitrogen. So those are really the main players of the elements of life. So elements consist of one type of atom. Gold is an example of an element. So all of the little tiny particles that make up gold are all of the same atom. So what is an atom? Well, an atom is a building block of matter. An element and its atom share the same name. An atom has a particular structure. There's a nucleus to the atom, and the nucleus contains protons and neutrons. Protons have a positive charge, while neutrons are neutral in charge. So protons are the positively charged subatomic particles located in the nucleus of an atom, while neutrons are neutral in charge, and they're subatomic particles located in the nucleus of the atom. Surrounding that nucleus, you have orbitals, and those orbitals are going to contain electrons. Electrons have a negative charge. Typically, if you have an uncharged atom, the number of positively charged protons has to equal the number of negatively charged electrons. And if this doesn't make sense right now, we're going to start drawing these out in just a minute. So for now, you can just kind of copy down the definitions, and then I'll give you some examples of what I'm talking about. Then we have the atomic number and the mass number. The atomic number is the number of protons in the atom. And this is how we organize our elements on the periodic table of elements. So they're ordered in increasing atomic number. So that's the number of protons. The mass number is the number of protons plus neutrons in an atom. So if we look at the periodic table of elements here, we can see all of the elements listed out here, and they're all in order of increasing number. So if we look at this right here at the bottom, we have hydrogen. The name hydrogen is actually spelled out, and then the symbol for hydrogen is H. And then up here you have the atomic number. And the atomic number, again, is the number of protons in the nucleus of that atom. And then you have the atomic mass, or mass number, 1.01. We can round that to just 1. And we can start to try to figure out how many protons, neutrons, and electrons are in an atom of hydrogen. So we said that the atomic number is equal to the number of protons. And then in an uncharged atom, it's also equal to the number of electrons. The mass number, or atomic mass, is equal to the number of protons plus neutrons. So if we have hydrogen with a 1 and a 1.01, this is our atomic number because it's the smaller of the two numbers, and this is our mass number. How many protons? Well, our atomic number is our number of protons. So there's 1 proton. How many electrons? Well, our atomic number is also our number of electrons if this doesn't have a charge. So in this case, it doesn't, so we have 1 electron. Now, how many neutrons? Well, our mass number is the number of protons plus neutrons. So 1 is equal to, and again we're rounding this, 1.01 is rounded to 1, so we have 1 is equal to the number of protons, which we have number 1 for already, plus the number of neutrons, which we don't know. Now this is a very simple math problem. 1 plus nothing equals 1, so we don't have any neutrons in an atom of hydrogen. But let's look at an atom of sodium. So if we look at sodium on the periodic table, sodium is here. You can see it has an atomic number of 11 and a mass number of 22.99, which will round to 23. So sodium is going to have 11 protons and also 11 electrons. And then to get the number of neutrons, we take our mass number is equal to the number of protons plus the number of neutrons. So 11 plus 1 gives us 23. Well, 23 minus 11 is 12, so our neutrons is equal to 12. So now that you get the idea of how to calculate these, now we have to actually start to draw them out. So if I want to draw an atom of sodium, I'm going to draw 11 protons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to draw 12 neutrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that's my nucleus there. And then I'm going to draw 11 electrons. And the electrons are found in orbitals surrounding the nucleus. The first shell, so these are the octet rules and the rules of assigning electrons to these orbitals. The first orbital, or the first shell, can only hold 2 electrons. The second and subsequent shells can hold a total of 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. So now what we've drawn so far is the 8 plus the 2 is 10. We have to draw one more orbital, and we only have 1 left on this outer orbital. This is known as a Bohr model of an atom. And there's different ways of drawing the Bohr model. Instead of drawing out the protons and neutrons in the center here, we don't really care about drawing out each individual dot because these dots are not going to be the ones that are going to form bonds with other atoms. It's the electrons in this outermost orbital that are going to form bonds with other atoms. And those electrons in the outermost orbital are known as valence electrons. So if we look at this periodic table here, we can kind of figure out how many valence electrons are going to be found in each atom based on what row it's in. Everybody in the first row is going to have 1 valence electron. So in group 1, 1 valence electron. In group 2, it's going to have 2 valence electrons. These transition metals do weird things and they have different exceptions and everything, so we'll kind of skip over those. But then in group 3, we have 3 valence electrons. In group 4, there's 4 valence electrons. In group 5, there's 5 valence electrons. Group 6, there's 6 valence electrons. Group 7, there's 7 valence electrons. And group 8, there's 8 valence electrons. Now in order for an atom to be happy, it wants to have a full outer shell of 8. So this one has this 1 floating out here. It wants to get rid of it so that it can have its full outer shell of 8. If this one does end up getting rid of an electron, it's giving up a negative charge. It becomes more positive by 1. Sometimes you may see sodium written in its ionic form, which is Na1+, or Na+1. So most chemists like to put in that 1+. Sometimes you'll see me writing it +1. But this is in its ionic form, which means it has lost this nuisance electron. It's given it up to something else in order to form an ionic bond. So once we get into bonding in the next section of this lecture series, we're going to learn about how bonds are formed, where this electron is going if it gives it up, and so forth. But for this section, hopefully you guys were able to follow along and you know how to calculate how many protons, neutrons, and electrons are in all of the atoms on the periodic table. And you're able to draw out the basic Bohr model of this atom. So when we draw this out, remember that the rules, I'll write out the rules for you. So the octet rule says the first orbital can hold 2 electrons, and I abbreviate electrons E negative. The second and subsequent can hold a maximum of 8 electrons. Again, in this next section that's coming up, we're going to talk about how these form bonds, what ions are, and ionic covalent and hydrogen bonds.